Welcome to Learning Math with Mr. Tan. Today I'll be talking about coordinate geometry, and before I begin, let me talk a little bit about my approach towards this topic. It's my personal preference, alright, to approach this topic in a way to introduce all three concepts at one go. And these three concepts that I'm talking about are namely the length of a line segment, the gradient of a line segment, and then the equation of a straight line. So these are the three main concepts within this chapter, and I personally prefer, and this could be different from some other teachers, I personally prefer to introduce all three of them at one go because there are many questions where, if you're given 2 points and its coordinates and you can just really find all three of them at one go. You could, for example, have a point A and point B, and then you can just find the gradient, the length, and then the equation of the line passing through them. So I believe that these three concepts are also kind of connected to each other, because from the gradient you can get the equation of a straight line, and then the length of a line segment actually helps you to understand the formula of the gradient. So, and in terms of the approach, in terms of the sequencing, I personally prefer in this case to talk about the length first, because that length of a line segment helps you to understand how did the gradient formula come about and why is it constructed like that, alright? And so that kind of helps. So that's my personal belief. So moving on, we will now talk about the length of a line segment. So to find the length of a line segment, we will go through this little activity together. Alright, we have this graph grid over here with point A here and point B. And we have a point N where it forms a right angle triangle with point A and B. And why is this right angle triangle important to us? Because we're going to use Pythagoras theorem to help us find the length of AB, which is the length of the longest side. And this right angle triangle will enable us to do that. So next, we're going to fill some of these things in. Okay, so coordinates of A is 1, 1. And I'm going to mark out here as well, 1, 1. Alright. And the coordinates of B would be 3, 4. Again, I'm going to mark out 3, 4 over here. Okay, so next we'll proceed to find the length of Bn and An. Alright, so the length of Bn would actually be the number of units between N and B, and that is quite obvious. That is 3 units. And how does that come about? So let's look at from point B, we are at the level of y equals to 4 over here, y equals to 4, and then along AN, this is y equals to 1. So this essentially is 3 units, right? So this is basically just taking 4 minus 1. So essentially, this 4 came from the y coordinates of B. Alright, and this 1 came from the y coordinates of A, which is also the y coordinate of N, but N is just a point to help us to use Pythagoras theorem, but we are more interested in point A and B, so we're just going to put it as y coordinate of point A. Alright, so next we have the length of AN. So this is also quite obvious. There is just 2 units between them, and let's see how to come about for this, right? So over here at A, we have x equals to 1, alright, and over at N, we have x equals to 3. So clearly we're just taking 3 minus 1, and this 3 came about from the x coordinates of B, which is also the same as x coordinate of N, but again, like I said, we are more interested in A and B. And the 1 came from the x coordinate of A. So we're not done for this part. Next is we will use Pythagoras theorem, alright, which is AB squared, which is the longest side squared, equals to Bn squared plus An squared. So that's basically just 3 squared plus 2 squared. And if you are interested in the final answer, that's going to be a 3.61 units. all right, to 3SF. But actually, this is not that crucial to us because we're trying to understand, okay, so what did we substituted into here? Essentially, these three came about from this part. Let me try to highlight this. These three came from taking the y coordinate of B minus y coordinate of A. Alright, and we square it. And then this 2 square came about from, again I'm going to highlight, x coordinate of B minus x coordinate of A. And again, squared. So yeah, now we try to come towards a generalization, and I'm going to remove the 2 arrows that were drawn earlier on to help you see what links to what. Alright, so I'm going to erase this and this, and I'm going to complete this with the square root. Oops. Alright, so the length of line AB essentially is just this formula. Alright. However, if you checked your textbook, usually you will see that it's written in a slightly different form. I'm just going to do some adjustments. Okay, so I'm just going to do some adjustment, and how it usually looks like is this x2 minus x1 square plus y2 minus y1 square. Alright, and it's not really particularly important whether x or y comes first because it's just an addition, and it's just you can just switch the 2 perfect squares around. But let me explain a little bit why I have used B and A earlier on as my subscript under the x and y, but now I've changed to 2 and 1 because usually for coordinate geometry questions, we are not just limited to point A and B. We could have point P and Q, M and N, J and K, and so on and so forth. So it will be a bit confusing if we use a subscript A and B. So therefore, we just do a little bit of adjustment. So what we will do is just, I'm just going to highlight the line that points this out. So if we're just going to let the x coordinate of A be x1, y coordinate of A be y1, so that's going to give us that, and then the x coordinate of B will be x2, and then y coordinate of B be y2, and then that's that. So basically it looks like this. Point A has x1, y1, and then point B is x2, y2, and then we just put the coordinates into this formula like that. Okay, and next we're going to talk about the gradient of a straight line. For gradient of a straight line, we need to change the formula a little bit because previously we have used a formula for gradient as rise over run, or for some teachers they like to use vertical change over horizontal change. Some they would even use height over base, associating it with the concept of a right angle triangle. But this is not going to be helpful to us in coordinate geometry because we are given precise coordinates of points, and so it's not so easy to pick out what is the height and base or the rise and the run. Alright, so we are going to revisit what we did just now. Okay, before we proceed, we have here, same thing, we have point A, which is x1, y1, point B, which is x2, y2, marked out already. And let's revisit this little point here. So I'm just going to use this diagram all over again, and I'm just going to erase all these things here. And recall that I marked the coordinates of A as x1, y1, and coordinates of B as x2, y2. Okay, and so we have earlier on seen how we subtract coordinates in order to find the height and the base, or the two of the sides of the triangle. So essentially, this side, which is the rise, all right, is going to be given by here, which is y equals to y2. Over here, y equals to y1. Right, so y2 minus y1 is going to give us the rise. Next, we also have the run, which is over here. The run, which is a horizontal change. That's going to be given by here, this point here. We're just going to take it as kind of like x2. All right, and then over here for point A is x1. So the run is essentially just x2 minus x1. So if we were to put this into the rise over run formula that we used in sec 1, we're going to get gradient equals to y2 minus y1 over x2 minus x1. So this gives us a very neat way of finding gradient of a straight line. So for example, if I were to be given A as a point 0, B as a point 3, 5, then we can just easily identify this as x1, y1, this as x2, y2. All right, and then we can just easily substitute this into the formula. But before that, let me just make this mention that I'm going to use m to denote gradient. All right, so m equals to y2, which is 5, minus y1, which is 2, over x2, which is 3, and then x1 is 0. So we will just have 3 over 3, which is 1. Right, so this is a very easy way for us to substitute coordinates in order to find gradients given the coordinates of 2 points. Alright, so how does this relate to equation of a straight line? Clearly, the general form of equation of a straight line, which is given over here, and I think some secondary 1 teachers will even have introduced this, is that we have the general form for equation of a straight line, which is y equals to mx plus c. Okay, and this is essentially called the gradient intercept form. Okay, whereby the coordinates, the coefficient of x is actually the gradient, right? So this is actually the gradient. Okay, and the c, the constant on its own, this is the y-intercept. And y-intercept is the point on the y-axis where the graph intersects with the y-axis. So just one last segment on certain very special cases. And these are the cases of horizontal and vertical lines. So horizontal lines, first of all, are of the form y equals to c. Okay, and the equation of the x-axis would be y equals to 0. Okay, so this, how to understand why is it that the horizontal line is y equals to c? Of course, it passes through c, first of all, right, over here. Okay, but more importantly, why do we define the horizontal line with y equals to c? Because everywhere along this line is basically the same y coordinates of c. Okay, so in that sense, you can understand that the defining thing about this line is that everywhere regardless of the x coordinate, is just y equals to c. Another way to look at it is it is c units away from the x axis, which is y equals to 0. So in between them, it is actually a difference of c units in that sense. Alright, and next we have also the equation of vertical line. So you can kind of extend your understanding of the previous part to this and say that, okay, so then now we have vertical line whereby anywhere along this vertical line has the same x coordinate of a. So the defining thing about this line would be x equals to a, right? And equation of y-axis being x equals to 0, right? And then this means that this vertical line x equals to a is a units away from x equals to 0. Okay, so last thing is very important fact is the gradient of the line parallel to x-axis. Alright, so the gradient of the line parallel to x-axis is basically the horizontal line, right? And if you were to look at the horizontal line, think of it as your horizontal flat ground, and you imagine you are walking, walking along this line. Sorry for the not so nice drawing. And imagine you're walking along this flat ground. There is really no steepness because we associate gradient with steepness, right? And so because there is no steepness, we consider that to be zero gradient, zero steepness in that sense. However, the discussion for a vertical line would be a little bit more complex and probably is a subject of another video kind of thing. It's not something I can just explain in 1-2 minutes. So we are just going to say that the gradient of the line parallel to y-axis, which is basically the vertical line, just write vertical here, is actually undefined. Okay, and one last pointer would be two parallel lines, a pair of parallel lines have the same gradient, right? Think of these two parallel lines as having the same steepness, right? So then it naturally has have the same gradient. Right, so thank you for watching this video. I hope this helps you to extend a little bit of your learning in terms of deepening your understanding of the concepts about the formula. And if you have any questions or any other concepts or anything you want me to do a video on, just drop me a comment and I'll do something about that. All right, thank you for watching. Take care. Goodbye.